After non-local simultaneity, the principles of relativity, the time dilation and length contraction effect, in this lesson we are now studying the Lorentz Transformation, which in special relativity replaces the Galilean Transformation. Let's briefly recap what the purpose of the Galilean transformations is. Imagine an event which happens at coordinate position x, y and time coordinate t in reference S, and consider a second reference frame S' in uniform rectilinear motion along the x-axis at a constant speed. In the instant when the two origins were overlapped, two experimenters, one at O and one at O', synchronized their clocks. Of course, S' does not stop, it is an instantaneous action. Of course, observers in S' will use different numbers x', y', t' to describe the same event. And the purpose of the Galileo transformations is to transform the y', t', x' coordinates in the reference frame S' into the x, y, and t coordinates that are valid for the observer in the S reference frame. Unfortunately, they are no longer valid. Let us see why. Let us see the reason why the Galileo relation t equals t' does no longer apply in special relativity. There are two reasons: an effect due to time dilation and an effect due to disagreement in clocks synchronization. Let us focus on the first one. Here we have the S reference frame, and a second reference frame S' is traveling toward the right at a speed v. As we know, an experimenter in S sees every clock in S' running slower. It is the time dilation effect. Now consider the case where the two clocks are located at the two origins, and that these two clocks were synchronized in the instant when the two origins passed each other, namely when the O' clock passed over here. If this is the case, every clock reading t' taken at O' simply transforms on the clock at O into a greater value t, which equals gamma by t', and this is the time dilation effect. But there is a second effect due to disagreement in clocks synchronization, and it takes place when the second clock is not located at the origin of the second reference frame, but it is at some point A' over here. Now, as we have seen, even if the two clocks, one at O' and one at A', are synchronized according to an experimenter in S', they are no longer synchronized with respect to an observer which is in the S reference frame, which contends that the clock at A' was started later with respect to the clock at O'. We have to do some calculations to compute the delay. Let us see the reason why we have this disagreement between clocks' synchronization in more details. Here we have our reference frame S. A second reference is in motion along the x-axis at a speed v, and we have a clock at the origin O' and a second clock at a point A', and we want them to be properly synchronized. As we know, the correct procedure to do this is to place a light source at the midpoint of the segment O'M', send out a light pulse, and in the instant when the light pulse reaches the 2 points, the two clocks start together. Now, to an observer in S, this is not true, because from his point of view, the clock at A' was started later with respect to the clock at O', and this simply because in the meanwhile the light pulse is traveling in the direction of A'. A' is receding from it, and at the same time O' is approaching the light pulse. Now let us evaluate the amount of this discrepancy. We'll denote by x' the length of the segment O' and prime. Of course, half the segment is x' over 2. To an experimenter in S, there is a length contraction effect along the direction of the speed, so that this length will transform into a shorter length, x' over 2 gamma, namely we divided x' over 2 by the gamma factor. And here the two halves of the segment are contracted. Let's do some calculations. Here we have our reference frame S and the moving reference frame S'. The experimenter in S will see A to be traveling toward the right at a speed v, while the flash is moving in the same direction at a speed c. Therefore, he will claim that the initial distance between M' and A' is reduced every second by c meters and contemporarily increased every second by v meters. Thus, between the light front and A' every second, there is an overall distance reduction of c minus b meters. Going from M' to A' takes light a time which is the initial distance over the distance reduction every second. Thus, x' over 2 gamma, which is the initial distance, over c minus b, which is the distance reduction every second. Exactly in the same way, the experimenter in S will see O to be traveling toward the right at a speed v, while the flash is moving at a speed c toward the left. Thus, he will claim that the initial distance O'M' between the light front emitted by M and O' is reduced every second by c meters and contemporarily reduced every second by v meters. Thus, there is an overall reduction every second of the distance of c plus v meters. Thus, going from M' to O' takes light a time which is given by dividing the initial distance by the distance reduction every second, so x' over 2 gamma over c plus v. If there were no difference between this time interval and this time interval, two clocks would be properly synchronized, but as we have seen, this time interval is longer than this one. Thus, the difference between these two intervals gives the overall delay, and to compute the delay we have to subtract the time to go from M' to O' from the time to go from M' to A'. Here we can do some calculations. We can factor out x' over 2 gamma, and here we can find the common denominator, which is c squared minus v squared, and if you do the calculations you are left with 2v at the numerator. Then we cancel off the two factor, we factor out v over c squared, and you are left with a v squared over c squared at the denominator and a factor 1 over here. Now we remember that this is the gamma factor squared, then we can write gamma instead of 1 over 1 minus v squared over c squared, and we get x prime v gamma squared over gamma. We cancel off one gamma factor and we get the formula for the overall delay between these two clocks. As we have said, the Galileo relation t equals t prime does no longer apply because of two reasons. The first one is an effect due to time dilation, t equals gamma t prime. The second one is an effect due to disagreement in clock synchronization. We have evaluated the amount of the delay, and it is gamma times x prime v over c squared. As it can be seen, the greater the separation between clocks in S prime, the greater the synchronization delay seen by S. Now we can add these two effects together and get the value t, which corresponds to a clock reading t prime in S prime. Thus t is gamma t prime, correction for time dilation, plus gamma x prime v over c squared, which is the correction for synchronization, and we get gamma times t prime plus x prime v over c squared. As we have seen, a clock reading t prime at a position s prime in the reference s prime transforms into a clock reading t in the reference frame S, and this is the relation between t and t prime. This relation replaces the simpler Galileo relation t equals t prime. So far for the time coordinates, but which is the corresponding relation between spatial coordinates x and x prime? Here we have our reference frame S. Consider an event that happened at a position x along the x-axis. The distance to the origin is, to an observer in S, a proper length measure. But if we consider the same event from the viewpoint of an observer in a reference frame S' in motion toward the right at a speed v, now to him the reference frame S is moving toward the left at a speed v, same magnitude but different direction. Now to the observer in S' there is a length contraction effect, and this measure x transforms into a contracted length x over gamma. But from the viewpoint of the observer in S', this distance x over gamma can be seen as the sum of the distance x' between the position of the event and the origin O' and the distance vt' that O' has traveled since the instant when the two origins were overlapped. Thus we have that x over gamma and x' plus vt' to the experimenter in S' are two expressions for the same distance, namely x over gamma equals x prime plus vt prime. And if we solve with respect to x and we factor out gamma, we get the transformations from the spatial coordinate x prime in s prime into the spatial coordinate x. We are now ready to write down the Lorentz transformations. After the Dutch physicist Hendrik Lorentz, Nobel laureate in physics in 1902. If S' is a reference frame in uniform rectilinear motion along the positive direction of the x-axis at a speed v with respect to another reference frame S, we have from S' to S x equals gamma times x prime plus vt prime, y equals y prime, since we have no length contraction effect along the direction perpendicular to the velocity, and t equals gamma times t prime plus vx prime over c squared. It can be proven that the converse relations from S to S' are the following. Only the sign over here and over here changes with respect to the first relations. Let's compare the Lorentz transformation to the Galileo transformations, which are easier. X equals x prime plus vt prime, y equals y prime, t equals t prime, and the converse relations. If we notice these two relations, there's just a gamma factor of difference between the Lorentz transformations for the spatial coordinates and the corresponding Galileo transformation. Let us derive now the Lorentz transformations for velocity. Consider a reference frame S, a second reference frame in motion with respect to S at a speed v, and a point particle in motion at a speed u prime with respect to S prime. And we want to find a formula that transforms u prime into the corresponding speed value for the observer in S. Now, u prime is equal to delta x prime over delta t prime. Of course, we know from the invariance of the light speed that one cannot apply the Galileo transformations for velocity addition, namely u equals u prime plus v. For instance, consider a distant star which is approaching to us at a speed v equals c over 4, and in the meanwhile it is approaching, it is spreading out light at a speed u prime that is of course equal to c in its frame of reference. So the frame of reference in which the star is standing still is what here we have called S'. Now, here it is the observer in S, the light emitting source is approaching to the observer at a speed c over 4, and the reference frame measures for the light speed a value of c. If the Galileo transformations applied in the frame of reference S, we would measure a speed velocity u prime plus v equals c over 4 plus c, which is equal to 5/4 c, and this value is of course greater than c. To derive the correct way to transform the speed u prime, delta x prime over delta t prime, into the corresponding value in s, u delta x over delta t, what we have to do is just write delta t and delta x by means of the Lorentz transformations. We have just to replace x with the corresponding interval delta x, x prime with the corresponding interval delta x prime, and the same for t prime. Here we have the Lorentz transformation for time. We replace t prime with delta t prime, x prime with delta x prime. Now for the particle speed u in s, what we have is u equals to delta x over delta t. Let us write delta x at the numerator over here, delta t at the denominator over here. Then we cancel off the gamma factor. Here we factor out delta t prime, and we are left with a v factor over here and delta x prime over delta t prime that replaces delta x prime. At the denominator we have something similar. We factored out delta t prime, so here we are left with a factor of 1, and here we have delta x prime over delta t prime and v over c squared. Now we cancel off delta t prime, and here we have u prime and u prime. We replace with u prime these two expressions, and we get the Lorentz transformation for velocity. U equals u prime plus v over 1 plus u prime v over c squared. So it is similar to the Galileo transformation for velocity, but we have this denominator now over here. Let us re-examine the case of a star moving toward us at a speed v equals c over 4. Here it is the star, which is approaching to us at c over 4, and in its reference frame it spreads out light at a speed c. And here it is the observer at rest with respect to the reference frame s. According to the Lorentz transformations for velocity, we will measure a light speed of u prime plus v over 1 plus u prime v over c squared. Now we have to replace u prime with c over here. We cancel off this c squared factor at the denominator, and we are left with 5/4 at the numerator and 1 plus 1/4, namely 5/4 at the denominator. We cancel off the 5/4 factor, and the final result is c. Thus, the light speed, according to the Lorentz transformations, is still c even in the reference frame of this observer s, in agreement with the relativity principles. Language of learning. You factor out a common term, or you factor an equation. We factor out the x. xy plus 2x equals x times y plus 2. On the other hand, you expand an equation. Let's expand the equation a times b plus c equals ab plus ac. It is the converse process of factoring out. You cancel off a factor. Let's cancel off the 3 factor over here and over here. You derive an equation, a formula for something. Let's derive a formula for the velocity transformation. You find the common denominator. Let's find the common denominator. 1 over b plus 1 over c equals c plus b over bc. And of course you solve with respect to x. Some more language of learning. You do calculations when you are literally doing math. To get the solution, you have to do some calculations. But you make calculations when you are assessing a situation. I made a quick calculation and I decided to have dinner out. You say reduced by, increased by. The distance is increased by 100 meters every minute.